Hi everyone, I'm An-Yeu from the National Taiwan University. As the last presentation in the AM section, my job is to keep it on time and make it simple so that you won't ruin your appetite. Okay, so I'm going to introduce the computer sensing and see how it applies to the IoT application, but I want to emphasize that it's not just for compression. So I got my degree in the University of Maryland, and I work in AT&T Bell Lab before, and I also work in E3 as a part-time appointment and supervising the WiMAX and the DSP processor project. And now I'm a board of government member in the Second System Society. So what is compressed sensing? In the past, we will sample every pixel of the picture, and we want to compress it using it like a JPEG or wavelet. Then we transmit over the channel, and at the receiver side, you also need to do the decompression. The compressed sensing want to finish the sampling and the compression within one operation. And the key concept is measure what should be measured. Therefore, we can save the cost and the latency during sampling. So one most important ingredient of the compressed sensing is the sparsity. This time series signal shows that at the first glance, you won't see the sparsity in this signal. However, if you take a Fourier transform, you will see that it has a very sparse component in the frequency domain. So that is if a signal X that can have some kind of sparse representation in certain domain, we can still apply the compressed sensing for his application. In this case, the psi is the so-called sparsifying matrix, or we call the dictionary. It's very important in our application. In this case, the FFT could be the psi for this kind of time domain signal. So how can we perform the compressed sensing? It's a very simple tutorial. Suppose we want to find a big black ball among the 10 balls. In the conventional sampling theory, we need to measure the 10 balls one by one. So it takes 10 sampling. However, if we randomly grab those balls, we make 3 pies of measurement. So we got a measurement of 102 gram, 5 gram, and 102 gram. That will make 3 equations. But this is, we have 10 balls, but we have only 3 equations. So it makes underdetermined problem. And fortunately, people in the signal processing society, they have built the whole theory for compressed sensing, so we can find the exact solution, even it is an underdetermined equation. So the whole framework should look like this. At first, we have the original data, like a 512 data. They were random sampled into a 128 measurement data. They were sent over the channel. At the receiver side, you need to solve this complicated equation, then to restore the data. So this picture shows some many important messages. Firstly, after the random sampling, we already achieved the compression. In this case, the compression ratio is 1/4. And secondly, you can see that the sensor side is very simple, but the receiver side is very complicated. So it's kind of asymmetric. But the light fits very well into the IoT application, because in IoT, we want to have a light sensor, but we have more computing power at the receiver side, also called the access point. So that's the reason why people start to apply the compressed sensing to wireless healthcare application. People will wear lots of biosensors, and they will transmit over the air for doctor's diagnosis or medical database storage. However, the limitation is the battery and the limited bandwidth. The compressed sensing can help with that. So that's the reason you will see many chip design. For the encoder, it's quite easy because you only need to perform the random sampling from this original EKG signal to this kind of compressed random data. So many chips, they have done the sensor in a digital way or mixed mode way. And they've also focused on like biomedical data like PPG and EEG. And for the receiver side, it's much more complicated. As I said, you need to solve this equation probably in computer, but it's better in your silicon. So the most well-known solution is linear programming. It's a basic pursuit, but it's very complicated and time-consuming. So most people use the greedy type algorithm like OMP, orthogonal matrix pursuit, or stochastic gradient pursuit. I won't go to the detail due to time, but this like orthogonal matrix pursuit, they solve the sparse solution through iterative operations, so it's more suitable for silicon implementation. So this shows the result. For basic pursuit, you can get very good reconstruction quality, but for OMP, the quality is a little graded, but still it's better for silicon implementation. Therefore, when you see the ICC paper, you always see they were built by the OMP method. And in our lab, we also developed a new reconstruction chip based on the stochastic gradient pursuit method. So compression seems to be the objective of the computer sensing, but what's beyond compression? So this shows a typical wireless e-health monitoring system. If we don't do any compression, we will have a massive sample data. Therefore, it will suffer from the DAC overhead, IO overhead, and ADC overhead. So people start to think even for the machine learning overhead. So if we apply the computer sensing, it seems like we can reduce the data amount. Therefore, we'll be happy in the DAC, ADC, and IF. However, at the receiver side, we still need to do the reconstruction. Also, you still have a massive data, so it's not good for your machine learning. So the key concept of the so-called compressed learning, I guess Yujie has mentioned that, is can I just eliminate the reconstruction stage, and I don't still use this small amount of data, the compressed data, and I send to my machine to make the decision, also called analytics. That's the key concept of this project. So the idea is if I don't want to do the reconstruction, I want to send my compressed data directly to the inference engine for the data analytics. So this is an application scenario for our development. Something like people wear biomedical sensors 24 hours a day. They want to do the automated detection. Once you find some abnormal situation, you will inform the doctor, and we will do the full reconstruction for the doctor's diagnosis. So there consists two parts. One is the edge detection. We want it to be light and simple. And we still want to keep the flexibility for doctor's diagnosis. So it shows the conventional way. We need to change remember the site, the specified matrix, also called dictionary. We can change this site in advance offline. And during the conventional way, we use the site to reconstruct our data. Then we send to the machine learning or SVM for detection. But we don't want to do this. On the contrary, we have developed a new technology. We call this class-dependent dictionary learning. That means we can separate the dictionary for signals and something like a noise or irrelevant signal. And with this newly developed dictionary, it's very easy to do so-called detection. Something like we will do the partial reconstruction. We can check if the signal is abnormal or not. Then if we find out the signal is abnormal, we will do the on-demand reconstruction for the doctor's full diagnosis. So it consists of two stages. First is fast detection. The other is a full reconstruction. And usually the abnormal case only happens with probability of 10 to 50%. So that can save our total cost in the whole system. So here's the experimental result. We test the data set in the NTU hospital from the ICU And we want to check if the patient has AF or non-AF. So here's the simulation result. We first do the partial reconstruction, and we can find out there are some sparse components in the AF domain, and we have 0 component in the normal domain. Then we can make, by this kind of energy comparison, we can detect the AF immediately. However, if we look at the waveform, it's not good enough. But the purpose is not to see the full waveform. The purpose is to see the detection. So we can meet the mission well by using this partial reconstruction. However, if the doctor still want to see the full waveform, we can send it to the second stage to do the partial basic pursuit. Therefore, they can find out all the sparse components and reconstruct the signal with high fidelity. That's the concept of this kind of two-stage reconstruction stage. The first stage is for fast detection. The second stage is for the full reconstruction. So here shows the simulation result. As we can see, the TDDI is our proposed mechanism. You can see the fidelity is not so good. However, the accuracy is the same as the original reconstruction-based method. That means the waveform, we can still make a precise detection by using our proposed mechanism. Also, because we have a two-stage reconstruction, we can save lots of complexity in chaining, also in inference. And these are the total saving we achieve. So in summary, in the first 2 years, we have created this kind of new framework. You can see in the conventional system, you do the reconstruction first, is A. Then probably you need to do the denoise or inference removal is a stage B. Then you send to the inference engine to check if it's AF or non-AF. But now with this kind of new framework, we can perform operation B and C in a compressed domain. That can save us lots of complexity. If the doctor still want to see the original signal, they can go to the A-plan. We can do so-called on-demand reconstruction. So we can still see the fully recovered signal. So these are the new framework we developed in the first 2 years. Now we are still working on how to refine the detail. The next issue I want to bring to you is more interesting. Is how to add the embedded security in the conveyor sensing. So in the IoT environment, well, we have lots of biosensor, but there are some cracker or eavesdropper who want to get your signal. So if you look at the signal on the left-hand side, you know this is a EKG. But if you look at the compressed signal, probably you don't know what it is. So that means compressed sensing itself has an inherent security feature. It's scrambled data, so it's not easy to see the detail of the original signal. So people already know this, so they develop some papers, but they try to redesign the sensing matrix, make it more complicated, or remapping the matrix. We find out there's still a problem. Firstly, it's a linear-based approach, so maybe it can be cracked by a plain non-text attack or ciphertext only attack. Also, if you change the memory sensing matrix, very often it will take you more memory, and you need to synchronize with your receiver. And if you still want to see the result, you need to still pay the complexity for your reconstruction. So this is not our direction. So what's our direction? We want to have a new method for the compressed domain analytics. We call it privacy preserving. That is, we transmit the compressed data, and we want to do the classification at the low compression domain. In the same time, if she attend this conference workshop or she read our paper, probably she can crack our data because she knows how we design it. However, now we want to find a way to add some perturbation at the compressed data. Therefore, we can still detect our data safely, but she cannot crack the data or make a right detection. That's the whole concept of our ongoing project. It's called the PPCA. So this picture is very interesting. That is, given an image, we can do the PCA, then we have a so-called eigenfaces. However, we can also perform the other analysis. It's called a linear discriminated analysis. We can get the visual faces. This is, I guess, that's very important. That is, for the eigenfaces, you can get all the information of these people. You can know his male, his age, and his rough appearance. However, if you receive a visual faces, you can know he's a male, but you cannot tell how old he is and what's his true appearance. So we think we should think a way to map our original signal to a more private space. We call that a space for discrimination, rather than for reconstruction. That's the whole some concept for our project. So how to do it? It's a little complicated, but I will try to explain easily. So first, we still use the PCA. PCA is a very good tool to reduce the signal reduction. So we still mapped our signal to the eigenspace on the left-hand side. And it consists of the AF and the non-AF signal. The next tool is LPP. LPP is a locality preserving projection. That can map the low signal onto a decision space. That means in that space, we can do a very good discriminative or classification. And then the next stage, we will use the SVD to create two spaces. One space is this one is a discriminative space subspace. The other is a so-called complementary subspace. So to visualize the result, I will show this one. Something like after we properly design the dictionary, you can separate the signal into two subspaces. One is on the top, which is red. You can see the amount is, the amplitude is quite small, it's 0.2. But you can roughly see that the first two epochs has more fluctuation, and the third one has less fluctuation. That means that's good enough to detect this is AF or non-AF. For the rest of the signal, it belongs to your basic heart rate and the basic other, like baseline wonder, that kind of thing. But they are irrelevant for your decision. So with this kind of signal separation, we can extract the signal directly to the decision space, which is called SD in this case. And for the red one, the green one, they are not directly related to the decision. So the detail, we have already derived some mathematics, so we can design this kind of matrix very easily. And after we receive the compressed data, we can go through this kind of dictionary, and we can filter out the decision signal for the SVN or other classifier. So the next message is, how can we just add more security on this framework? Yeah, the answer is yes, because now we know the key information is in the SD, and the irrelevant information is in the complementary information. So probably we can add some perturbation signal on the SC, complementary information. It will corrupt the whole signal, but still retain the necessary information for your decision. So we can add, because they are independent, so you can destroy the red, green one very easily, but without affecting your decision. So that's the whole concept of privacy preserving compressive analytics. So here's the last slide. Okay, I'll make it short. So how to read this? the x-axis is the SNR. The SNR, this size means that we just inject a small perturbation. If the SNR is low, that means we inject lots of perturbation. You can see from the red one first. The red one shows so-called mutual information. The mutual information of the original signal and the corrupt signal should be less. So it's very good for encryption. As we can see, we add more perturbation, the SNR drop down, and the mutual information also drop down, the red line. So that means the perturbation is very good to protect our data. And how to read the other two lines? The first line is on the top, is our mechanism. That means even though the mutual information or our signal is corrupt, we can still keep very high accuracy for our detection. And the middle one is the eavesdropper's result. Probably she knows she knows our mechanism or she tried to crack our signal. However, remember two things. First, we didn't transmit all the original signal. We only transmit the discriminative information. So she cannot get very good precision. That's the first thing. The second thing is because we added the perturbation. Okay? So you can see the SNR, if getting worse, her accuracy is also getting worse. So that means we can protect the original signal while we can keep the very high precision for our encrypted data in the compressed sensing domain. Okay, so I guess, okay. So this shows, kind of summarize my presentation. So we know the conventional system, you need to do the referral reconstruction, maybe you need to do the denoise, then you go to the inference engine. But now we have some initial trials, so we can perform all the things in the compressed domain. Now the new concept and the very interesting feature is we can add some perturbation to the compressed data, so it can be privacy preserving, and also we can send to our compressed analytics engine for detection, face detection. So in summary, I guess compressed sensing is a new DSP tool that can open the locked doors for many different kind of problems. As long as your problem has a sparsity, you can use this kind of new tool. I guess the famous example is the MRI image. And also, in our lab, we also apply it to the channel estimation of millimeter wave communication. And we have presented that now we can eliminate the reconstruction stage and make a new framework called the compressive analytics. We use the EKG signal to test our case, so we can do the faster detection of AF and NRF signal. And right now, we try to, based on all the analytics and the framework, we want to add the privacy. The perturbation can reduce the mutual information of the signal. However, it can still keep the accuracy for our detector. We think it will be very useful for our application in iFactory. But right now, we still got a homework I get from Vida and from all the Intel champions. So how can we apply this kind of framework to other kinds of signal? We have some thinking right now, and we try to provide our solution probably by the end of in next quarter or by the end of this year. So this conclusion talk, and yeah, our lab sometimes has a retreat. So we figure out the framework in the mountain, but sometimes we find out the privacy preserving while we snorkeling in the sea. So we also discuss under the sea. Okay, so let's end my talk.
Any questions?
Hello, I'm Chinnan from UC San Diego, and it's very interesting to hear your talk on privacy preserving, but I'm still not clear, because usually we evaluate that kind of approach by how hard it is to recover the identity of the subjects instead of how you too hard to separate the perturbation and hide the information. So could you comment on if you have any attempt to see how hard it is to recover the identity? Yeah, thank you.
Okay, the concept is you have an original signal, and you can reduce the signal to certain domain, right? So keep those information only for your decision, or so-called for utility. So in my presentation, actually the paper will be published soon, so you can see the detail. We use a sequence of a signal decomposition. First is PCA, then LPP, and then SVD. That means the original signal is 512 point, then in the compressed sensing now becomes 128, right? And you find out among all the 128 signal, only 30 dimensions is related to your decision. So something like you can play with. You keep the 30 dimension for your decision, and then you can add some perturbation at the rest dimension. Therefore, altogether, they will just camouflage all the signal, but while you can still retain the original signal. So that's the whole concept. And all the mathematical tool can support this kind of duration.
So my question is on the compressive sensing part. For the application that you have, you gave some performance numbers in percentages for both complexity reduction and size, bandwidth, data size reduction. Could you also comment on the absolute numbers and how many streams would it take to saturate either the bandwidth or the compute power on the platform that you ran it on?
You mean how much?
Yeah, I'm trying to see how heavy the workload is so that it requires this kind of compressed domain.
Okay, a rough number like probably you can think about if I'm decision making still SVM, right? If you even the compressed sensing can help to reduce, right? But you still need to restore it back to 512 data. Then you send to SVM. Now the input of signal is only 128. So the input size of our SVM already reduced a lot. So you can calculate the complexity. You can see it's very good to do the analytics in the compressed domain rather than in the restored domain. That can be a rough estimation of the computing resources.
Sure, but do you have a number of how many concurrent streams you can support with and without your scheme?
Concurrency?
Concurrent streams from multiple sources. I would guess that one of them.
Concurrent, okay. I think it should be okay for 10 or 20, something like that. It should be no problem. Especially now we have a chip, right? So we can, the final goal of this project is not just write down a MATLAB subroutine, right? We want to build a chip to solve all the things online. And the final goal is so-called uncensored analytics, but based on the compressed data, not from the Nyquist sample data. So we'll move to that direction and with a chip implementation. So that should be fast enough to handle hundreds, tens to hundreds of signals simultaneously.
Thank you, Professor.